This is part 5 of the polar graphing and area series, and this time we'll talk about intersecting regions and how to find the area in those cases. I am going to assume that you've already watched the first 4 videos of the series. So, okay, here we want to find the area that is inside r equals 1 minus cosine theta and outside r equals 1. If you need to take a moment to graph r equals 1, we haven't graphed it yet, you could do that, but it is just a circle with radius 1. So that would be a graph of this region here. So first we need to figure out where we are starting and ending our slices. So remember, when we integrate over areas that are not quantities that are changing and they're not constant, we're dividing it up into tiny little intervals and we're finding the area on each one of those intervals. So let's first by figuring out where are we going to divide up our intervals for this problem. So this is going to happen where these curves intersect, right here and right here. That's where we need to start drawing our slices because that's where the shaded region is. So all we need to do is solve when these intersect, which is when 1 minus cosine theta equals 1. So cosine theta equals 0. And so we know that that's going to happen when our angle is at pi over 2 and 3 pi over 2. So what will our slices look like? So let's ask that next because really these are a little bit hard to work with. So let's ask, what are they going to look like? And remember, all of our slices are coming from the origin. We can't slice outside of the origin and use our area formula. So here's our slices starting at pi over 2 and running down to 3 pi over 2. So let's zoom in and take a closer look. Okay, so we know if we just take one of these random slices, if we want to find the area, we're going to do of this slice will be 1/2 r squared d theta. And this slice goes out to the blue line. So our radius for this slice is 1 minus cosine theta. So we plug that in, and that gives us the area of that slice. Now let's look at this slice inside. This is also the area of this slice will be 1/2 r squared d theta. But this time it's going to the green curve, and so our radius is going to be 1. And so we get the area of that slice. So if we want to find the area of the shaded region, then we'll have to subtract the area of the blue slice minus the area of the green slice. So we see that we will do that for our entire interval from pi over 2 to 3 pi over 2 and put that formula in and we get the area of that region. And so now if we want to find an area where they intersect, it's going to look like this. And so we want to find the area of the shaded region. Again, we should ask which angles are we integrating over? Where are we making our slices? From what rotations do we go through? So if we start at 0, our shaded region will start at 0. And we're just kind of envisioning a little arm going around, kind of taking data. Is it shaded? Is it shaded? Is it shaded? And all of these answers are yes. And so we continue on. We see that we did take shaded region around the whole, like our data told us, yes, this area is shaded around the entire circle. So it will be a full revolution of 2 pi. So what are these slices going to look like so that we can figure out a formula? So let's zoom in and start making our slices from theta equals 0. Now we're only going to slice in our shaded region. So we only sliced in our shaded region, and we can see that from negative pi over 2 to pi over 2, the slices look the same. So they all have the same radius, and that is the 1 minus cosine theta. And so this region, if we just take the area of this region here, it would go from negative pi over 2 up to pi over 2 of this 1/2 r squared d theta. And I'm just going to go ahead and answer because you might be asking, why did you do negative pi over 2 and not 3 pi over 2? How did you know to change that angle? And I'll tell you, because our integration bounds always move from smaller to larger. So we're always moving from our smaller angle to our larger angle. So we could not move from 3 pi over 2 to negative pi over 2 because then we would be moving bigger to smaller. So let's see where we're at with our area. So we've found this area so far. And so let's record that and move on. Okay, so now let's continue from where we left off, and we're going to start making slices now for the leftover shaded region. So that is from pi over 2 down to that bottom angle, negative pi over 2. And these slices look the same until we get to 3 pi over 2, meaning that they have the same radius. So from pi over 2 to 3 pi over 2, all of these slices are going to have our radius as 1. And so we can form our integral going from pi over 2 to 3 pi over 2 of 1/2 r squared d theta. And again, why did I just switch my negative pi over 2 to 3 pi over 2? Again, because I have to move from smaller to bigger so that my d theta stays positive. And so we see that we now have found these shaded regions. And so our area is just going to be our first shaded region plus our second shaded region. And that is it. That is the full series. And so I hope you enjoyed, and I'll see you next time. Bye.